Good evening and welcome everybody, this is Obi-Wan Pez, Ren Simplex Pachinko. We're up to some math tonight, so as soon as I figure out what I want to do over here. Alright, well, happy Pi Day everybody. Silver! Good evening. What's up? Why not Tau? Get out. No, even the Tau people are welcome here. That is also a very good question that I don't necessarily have the answer to, however. Ooh. I was looking up. Here we go. On cutthenot.org, we have something called the Spigot Algorithm. Which was developed by Ramanujan and Vagan. Oops, T. In 1995. Okay. Fundamental idea is that of base conversion. So an algorithm for conversion between bases exists. Algorithm will generate the digits sequentially, one at a time, and does not use the digits after they're computed. Recent in some sense of the word, anyway. All right, so so there is a series pi as an infinite sum So here we go from term 0 through infinity, where we take I factorial and then multiply by 2 to the I plus 1 and divide it all by 2I plus 1 factorial. This by itself is not like exceedingly efficient, but it works pretty nicely. As it turns out, right, this can... That's a square. Oops. Oh, goodness. This can also be written as pi over 2 is equal to infinite sum as I goes from 0 to infinity of I factorial, so whatever number we're currently on, divided by 2I plus 1 double factorial. Now what this means here is that this is actually going to skip every other. So here, this is going to be equal to 1 plus 1 over 3 plus 1 times 2 over 3 times 5 plus 1 times 2 times 3 divided by 3 times 5 times 7. And so on and so forth. Right, this is actually infinitely long. Alright, and then not helpful. Alright, and then Horner discovered that you were able to write infinite sums in terms of repeated fractions. I'm not sure exactly what qualifications that had. Like, is it only on some of them? Does it work all the time? Let's see. William George Horner described in 1819. So this is a little less recent, over 200 years ago. And fairly useful hand calculation. Alright, so Horner in 1819 discovered a sub 0 plus a sub 1 x to the first plus a sub 2 x squared plus a sub 3 x cubed plus going all the way out to a sub n x to the n can be rewritten instead as a sub 0 plus x times the quantity a sub 1 plus x times the quantity a sub 2 plus x times the quantity a sub 3 plus x times the quantity, and so on and so forth until we get to the inside here, which is, alright, so a sub 4 plus dot 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 x times a sub n minus 1 plus x to the n. Nope. That's not That is neither an exponent, nor is it actually supposed to be there. X times a sub n. All right. And for the night, we're enjoying some rather smashed pie, but nonetheless, it is pie. It is pie day, so gonna enjoy what we got. Woo! King Uzoma, good evening and welcome. Sure. So 3.6 chain rule. Oh. Oh, goody. Well, there's a reason Calc 2 is like not super awesome. Bertram, what's up? Alright, so within the chain rule, we're talking about wanting to look at a particular Alright. So here we go. So what we want to take y prime of this particular y function. It is big, it is ugly, and it is nasty. But nonetheless, what we're looking at is just one gigantic composed function. Or rather, 1, 2, 3, 4, 5-ish composed functions, all stuck into each other. Yeah, and if anybody, if I just randomly disappear, I do apologize. I have been having some, issues with No. Generally speaking, I don't do too many of the problems that are directly out of the book. Because, especially if it is literally a question that is out of the book that is on someone's homework, then I don't do homework for people. So no, it's all right. But we'll make something similar. So really what we've got here is a sine function. And we want to take the derivative. Oops. I'll erase. All right, so we do d dx of the sine of u. And we just call it u. Yeah, we let u be equal to all that stuff that's just inside the sine function. Everything in there. No matter how ugly and nasty it gets. That's just what we let u be equal to. So then we can say, well, this isn't really... This part right here is not really a function of x anymore. It's now a function of u. So what we can do is we can split our d dx into d and dx like this, and introduce our new variable u both here and here. This allows it to divide out, so it didn't really change anything. It's just d dx when you put all this stuff back together. Oops. And then our sine of u technically goes right in here then. Because this is a differential operator, it really should be right next to the... Should be really right next to what it's operating on, and not stuck somewhere in the middle. So let me actually just rewrite it. So we're going to say that this is now d du of the sine of u, and then this is multiplied by du dx. Right. So u is this big, nasty, ugly thing here. This big, ugly, nasty thing here. And then we can say, well, we know what the sine of u is going to be derived as. Right? That's going to be equal to the... Nope. It's not the sine. It's going to be the cosine of u. And then we're multiplying by du dx. Well, now we have this u thing, which is, again, this big, ugly, nasty thing up here. So we can let, you know, v, or something else, equal the hard part of this. So this can be all the square root stuff. So then this is going to be equal to the cosine of u times, and we could do the same thing here. This isn't really a function of u anymore because of all this stuff. We can now let it be a function of v. So now we want dv of 4 minus 5v. And then this is going to be multiplied by dv dx. We just keep going at this over and over and over again until we get, you know, the result at the end that we want, which is going to sink into, you know, all of this stuff. So this is going to be equal to the cosine of u times, we take the derivative with respect to v of 4 minus 5v, it's going to just be negative 5, times dv dx. Okay, now we do the same thing again. All of this stuff in here, inside of the square root, can be w. So 3x squared minus cosecant of pi over 12 times x to the third. Alright, so w is going to just be all that stuff. And again, v is the square root thing. So this is going to be negative 5 times cosine of u times dw of, this was the square root of w, times dw dx. Now what's the practical upshot of all this stuff? Because if this is just getting too much, that's perfectly fine. I don't really blame anybody for saying, no, that's just too much stuff. What you can do instead is, again, just think of this as nested functions. So you've got to go all the way down and say, like, okay, at each individual step, we have to take the derivative of the thing that's here, and everything that's inside of that function is just going to get copied in the derivative over and over and over again. Yeah, I'm using, like, or I used a question from volume 1 to inform this particular one. Hello, Ims. Okay, so our ddw of the square root of w is going to be, this is w to the 1/2, so we drop our exponent down, and that is now times w to the negative 1/2 times ddx of 3x squared minus the cosecant of pi over 12 x cubed. So let's do this last one just without changing anything. So with this is going to get us a negative 5 cosine of u over 2, so negative 5 over 2. Times, this is going to be 1 over square root of w times, and then here, all of this stuff, we take down the 2, that's going to make a 6x minus, parentheses, the derivative of a cosecant is a negative cosecant of all the stuff that's in there, cotangent of all the stuff that's in there. Okay, and then all of this stuff, cosecant, cotangent, it can be either on the outside of the cosecant, cotangent parentheses or on the inside, it doesn't really matter. It's all multiplying by the derivative of the inside. So our pi over 12 times x to the third is going to become 3 pi over 12 x squared. So it's the derivative of that thing. Okay, so I saw number 236 or whatever said it was the square root of 6 plus secant of pi times x squared. Oh, 238. There you go. Sorry. Woo. All right. 239, yeah. Sorry, we'll get that next. Oy. Okay. So this is then going to be the cosine of all of this stuff. 4 minus 5 times the square root of 3x squared minus cosecant of pi over 12 times x cubed. Okay, after the cosine is times 1 over the square root of everything that used to be in there. So 3x squared minus cosecant pi over 12 x cubed. Alright, multiply by 6x plus cosecant pi over 12 x cubed cotangent pi over 12 x cubed times pi over 4 x squared. So coming all the way back, that's what that's going to be. And if your teacher wants you to simplify this in any way other than combining the constants, no. Just no. Right, the pi over 4 and the negative 5 pi over 2 at the beginning. No, it's alright. 6. I just click something. It's always a great idea. Make sure you click things. That was weird. Answers are always supposed to be big. Yeah, see, answers get to be that big when I make stuff up. Alright, dy dx equals 18. When x is 2, find f prime f4. Gets worse when I'm making stuff up in the higher Calc 2 and differential equations, because then it's usually like, oh look, we can't do that. Doesn't actually work. Who'd have thunk? Whoa. I just jumped like half the screen away. That was weird. That's where the mouse was. Apparently had some tension in the line or something. Just pushed it. Okay. So, so to get f of 4 is 6. This is telling us that 6 is equal to f of... Nope, that's not right. A. So null space is the vector for which you will get zeros, no matter what you do. Or multiple vectors. Also known as the homogeneous solution. Alright, so here. Okay, dy dx is going to be equal to 18 from our given. Dy dx as a whole up here is going to be equal to, here we've got a power rule, so our 2 is going to come down. And then this leaves f of u plus 3x raised to the first power. Then, attached to it by multiplication, we're going to get the derivative of everything on the inside here. So this was f prime at u times du dx plus 3. Okay, so we've got an 18 is equal to 2 parentheses f at u plus 3x times, this is, right, f prime at u multiplied by du dx. U is up here, so du dx is going to be 3x squared, parentheses, 3x squared minus 2. And then plus a 3 all the way at the end. That needs to still be multiplied. Here. Okay, so then here we can divide everything by 2 because that's all well and good here. So that's just going to be 9 is equal to. Here we want f prime at 4. So we want that term to be f prime at 4, which means that u is equal to 4. So now we have f of, that has to be 4, plus 3x, and x specifically is going to be 2 for this. And if you're like, why is it going to be that? Why isn't it maybe going to be changed or something like that? You can also go back up to u here and say that our u value is supposed to be 4 and our x value is supposed to be 2. So real quick, we could just plug in 2 and make sure that this comes out right. So here, 2 cubed is going to be 8 minus 2 times 2 is 4. So we end up just getting 4. So u equals 4 when x equals 2. That's more of a verification step than anything else, making sure that we're actually going to get what we think we're going to get. Make sure nothing is just weird. All right, and then here, parentheses, this is 3 times 2 squared minus 2 plus 3. Okay, from above, we know that f of 4 is equal to 6. So this is going to be 6 plus 3 times 2 is 6 times the quantity, f prime at 4, times, here we're going to get 2 squared is 4 times 3 is 12, minus 2, end parentheses plus 3. End parentheses. Alright, so 9 is equal to 12 times the quantity, f prime at 4, the unknown value, times 10, all plus 3. So here this is going to be 9/12 or 3/4 is equal to f prime at 4 times 10 plus 3. So we're going to subtract 3 from everything. So negative 3 plus 3/4 is negative 2.25. Can convert back to fractions in just a minute here. Alright, so that's going to be 9/4. Negative 9/4. Yeah. It's going to be equal to f prime at 4 times 10. Divide both sides by 10, you get a negative 9/40. is equal to f prime at 4. Alrighty. Woo! Yeah, no problem. Thanks again for stopping in, everybody. If you do have any questions, let me know. I'm gonna grab this differential equations book right here. Basically, anything that I'm going to describe using matrices, I'm probably going to start by using differential equations example, because it's just more or less where I always come from. When you've taken a differential equations class of some kind or another for, you know, basically 2 full years of your life. That's okay. Alright, so one example might be we have the matrix 1, 2, negative 4, 2, 1, 1, and negative 1, 3, negative 11. Set up with x1, x2, x3. And this is equal to our 0 vector. So any solutions to this system, x1, x2, x3, will form our null space. Yep. Mostly integration, if I'm honest. Alright, so all of our null space solutions will satisfy the above equation. All that we have to have well, not really. So differential equations are equations which have differentials in them. So really, we wrote a differential equation earlier. Right here. Where we said y prime is equal to all this nasty stuff here. All that, like, the only weird thing that doesn't exist in differential equations is we try as much as we can not to have stuff like dy dx. We try, generally speaking, to have our dy on one side and our dx on the other, with all of our y's with the dy and all the x's with the dx. So we try to make everything separated first, and then once you've got it separated, it's much easier to solve. And you've got your differential, your dy or your dx. It's already with the variables of its type. So it makes it a little bit easier to work with. Okay. So the null space solutions are the vectors which will get us are the vectors which, when input into this equation with x1, x2, and x3 in this location multiplied by our A matrix, our 3 by 3 matrix, you're gonna get 0, like no matter what you do. Yes, thank you. The trivial solution is 0, 0, 0, but it is very boring. Alright, I just wanted to make sure of something. So, one way to get the null space solutions is to just solve for x1, x2, x3 as is. So you can get some sort of solution which is going to come up with these particular values to get 0, 0, 0. The way that we typically do this, I hope I'm not completely wrong about this, but I thought. Yeah, right. Alright, so the way we usually do this is we say, okay, let's take the determinant of our A matrix, which we call that one, minus lambda times an identity matrix of the exact same size as A, and then set all of that equal to 0. This is going to get what we call our eigenvalues. I don't really appreciate eigenvalues at all till much later, but mostly when I needed to start teaching this. And it's going to get us our eigenvectors. Xi. Okay, so we take this as 1 minus lambda, 2, negative 4, determinant, 2, 1 minus lambda, 1, negative 1, 3, negative 11 minus lambda. Set that determinant equal to 0. Okay, so determinant of a matrix is not always the most easy thing, but in this case it's not too bad. The thing that I want to show up the least is probably the negative 11 minus lambda, so we'll use that. We'll use the bottom row, I think. Okay, so what we're going to do here is we take negative 1, which is this value here. Then we're going to essentially cross out the row and the column that are attached to it and say that we want to take the determinant of what's left. So 2, negative 4, 1 minus lambda, 1. So times the determinant of 2, negative 4, 1 minus lambda, 1. Plus 3 is here, and we're going to multiply that by the determinant of, again, cross out what's here. And wherever you started from, so like your 3 in this case, this is essentially going to be like kind of above and... So there are several ways to do this. One is to take whatever you see that's left and just write it out. So the stuff over on your left becomes the left column, the stuff over on your right becomes the right column. The problem with this is you have to memorize this weird plus-minus checkerboard pattern. I don't like it. It doesn't make any sense to anybody. I mean, it sometimes makes sense, but I don't like it. And again, it's the memorization thing. So instead, what I do is I go from my circled one, I go down and right, in which case there's nothing here, so I circle around to the top here. I'm going to start with this as my top left item. So it's going to be -4 here and 1 underneath it, and then the other column is going to be 1 minus lambda and 2. So I use the wrap method rather than the checkerboard method. It ends up getting you the same thing in the end, but nonetheless. Okay, so then that's fine. So again, we're just going across the row here. Okay, so when we cross out this column and then go from the 3 that we're using as our Mr. I love BBQ chicken. Evening. So when we're going from the thing that we have selected here in this particular row to be our coefficient out front, then again we cross out the column, cross out the row, can't use any of these numbers, and I go right and then down, and if that causes me to wrap, then I will wrap. So it goes to the nearest, it goes to the next element. In this case, it wraps around to the top. So we got -4, and 1 minus lambda is the next thing to the right, which again causes me to wrap around this way. You still can't see this. See? See? Knew I was going to do it. Alright, so this causes me to come over here. There's nothing here, so I wrap around to the top. This is now my top left corner. And then to get my thing to the right, I go to the right, but then there's nothing here, so I wrap around the other way. Misahide, how's it going? Alright, and then we do another plus. And we get on the outside -11 minus lambda times the nope. Determinant, there we go, of, and again here, cross out the column, cross out the row, it's this block here. So again, from this particular point here, I go right and down. Well, I go to the right, I can't stay here. Wraps all the way around. And then I need to go down, so I go down, but then there's nothing here. So I circle back all the way to the top again. So that's going to be 1 minus lambda, 2, 2, 1 minus lambda. Okay, is equal to 0. When we come down, -1 is going to be multiplied by, the determinant of this is by taking the main diagonal and multiplying these values, and then subtracting the off diagonal product. So how does that work? In this case, we're going to get 2 times 1 minus 1 minus lambda times -4 plus 3 times the quantity -4 times 2 minus 1 times 1 minus lambda. And third one, plus -11 minus lambda times, this is going to be 1 minus lambda squared minus 2 squared equals 0. So in this case, we end up with -2. Here are negative and negative, make this positive. And then we get a -1 from the outside, makes it negative again. 4 times 1 minus lambda. Okay. Next term is going to be -8 times 3 is a -24. And the negative here can come in to make this a positive 3 lambda minus 3. Plus. Alright, in this case, our 11 and lambda are both negative, so we can pull that out and switch the signs of the stuff that's in the parentheses. I guess. We'll just make this a negative out here instead. It's fine. Plus lambda. And on the inside of the parentheses, 1 minus lambda squared is going to be a lambda squared minus 2 lambda plus 1. And then this is a minus 2 squared is a minus 4. Alright, so minus 2, minus 4, plus 4 lambda, minus -24 and -3, it's going to be a minus 27, plus 3 lambda, minus parentheses, 11 minus lambda, plus 11 plus lambda, times lambda squared minus 2 lambda minus 3 equals 0. -6 plus, this is 4 lambda and 3 lambda is going to be 7 lambda. Minus 27. Alright, 11 plus lambda times lambda squared minus 2 lambda minus 3 is going to be a lambda cubed. This is going to be 11 lambda squared and also minus 2 lambda squared, so plus 9 lambda squared overall. Just lambdas are going to be -3 and -22. So -25 lambda. And then 11 and -3 make a -33 for constants. Okay, recombine. 7 lambda minus 33. Minus lambda cubed minus 9 lambda squared plus 25 lambda plus 33. Negative lambda cubed minus 9 lambda squared. 25 and 7 is going to make a plus 32 lambda. And plus 33 minus 33. Going to get a 0. Oh, that's nice. So this is going to get us a negative lambda pulled out. Positive lambda squared plus 9 lambda minus 32. Oy. Now, unfortunately, 32 is made up only of even numbers, so we can't get an odd value. That seems bad. I mean, not like that bad. But alright, so negative 9 plus or minus the square root of b squared minus 4ac all over 2a. 4 times 32 is going to be 128. That's a negative 32. Multiplied by a negative 4 is going to get us positives in those places. 128 plus 81 should be 209. Ugh. I don't want to do it. All right, let's see. 1, 2, negative 4, 2, 1, 1, negative 1, 3, and negative 11. Alright, so 0, 1/2 of negative 9 minus root 209 and plus root 209. Yep. Okay, so those are at least correct. Got eigenvectors with it, which is gross. But so one of the ways in which you can solve for eigenvectors is by taking each of your eigenvalues, which, if you remember, one of them was 0, so we'll go with that one. When lambda is 0, we end up getting our matrix that we started with. So 1, 2, negative 4, 2, 1, 1, negative 1, 3, negative 11. And we assume that we want x1, x2, x3. And it needs to be equal to the 0 vector. So then here we can augment the matrix. 1, 2, negative 4, augment 0. 2, 1, 1, augment 0. Negative 1, 3, 11, negative 11, augment 0. And by doing standard row operations for standard matrices, we should be able to show at least one of our eigenvectors, which I've got it here, so hopefully I get the right thing. Alright, so we're going to take row 2 and add twice row 3. It's already got an opposite sign in the first column, so that'll help get rid of it. And we'll take row 3 and add row 1 to it. And it will become the new row 3. So 1, 2, negative 4, augment 0. Okay, so row 2 plus twice row 3 is going to be 0. Row 2 plus twice row 3 is going to be 6 plus 1 is 7. Row 2 plus twice row 3 is going to be negative 22 plus 1 is a negative 21. And then at the bottom, row 3 plus row 1 is going to be a 0. It's going to be a 5. Negative 4 and negative 11 is going to be a negative 15. Interesting. So we should be getting something that's linearly independent, but those last two are showing me that this is linearly dependent. that's going to be a problem. So it's supposed to happen like this, and it's fine. All right, let's see where it takes us. So we're going to take 1/5 of row 3. Going to take 1/7 of row 2. One, 2, -4, 0, 0, 1, -3, 0, 0, 1, -3. Alright, row 3 minus row 2. Ends up with all zeros in that one. Here we want to take row 1 and subtract 2 row 2 to get rid of our second term. So 1, 0. Row 1 minus 2 row 2 is going to be a positive 6 plus -4 is going to be a positive 2. 0, 1, -3. Alright, and 0, 0, 0. So what we've got here is now 1t1 plus 2t3 is equal to 0. And 1t2 is minus 3t3. This really should be x's, just to stay consistent. Equals 0. So it says that x1 is equal to a -2 x3 and x2 is going to be equal to a positive 3 x3. And if we let x3 be equal to some dummy variable like t, then what we get here is that our x vector okay, so if we let x3 be t, then x2 is going to be 3, x3 is t, and x1 is going to be -2 times x3, which is t. So now we have our eigenvector, -2, 3, and 1. And then let's just multiply by t. Alright, so that's going to be one of our eigenvectors, which if we plug it into the original equation, it's going to get us 0, so 0, 0, 0. Therefore, it is part of our null space solution. All right. Anybody have anything they want to go over? Anything they want to talk about? Alright, we're talking about the Horner algorithm to shorten up our infinite series here. And one of the ways it worked to shorten things up. Nope, I don't want that one. $245 to $251. Okay, so this says, for the following exercises, use the information in the table to find h prime at a for the given value of a. So you have h of x is equal to, for instance, f of g of x. So you want to find h prime at x. Then this is going to be our chain rule that we need from this. So this was f prime at g of x times f prime of g of x times g prime at x. This one's 245. So you're going to go through every example basically the same way. You're going to find out what the derivative of h is as the derivative of whatever function they give in terms of f prime and g prime and the original f and g as well. Then at a point that is picked, so for example, if a is, let's go with a is 2. Then here, h prime at 2 is going to be equal to f prime at g at 2 times g prime at 2. So we can go onto the chart, figure this out. So g of 2 on the inside of the function, g of 2 is 1. Times g prime at 2 g prime at 2 is -1. Then we have to do f prime at 1, and f prime at 1 is equal to -2 times the -1 that we had from the previous step is going to get you a value of 2 for h prime at 2. Yep, no problem. So you're going to get all sorts of crazy fun crazy fun derivatives there. There is the possibility that some of those don't exist, just because if, for instance, we got like f of 2 is 4, but then there's no x value that's 4. So if it was like, you know, g prime of f of 2, then what would happen is you've got f of 2 on the inside, which gets you 4, and then g prime of 4 is undefined. And so it would stop you right there and say, well, I can't do that. Now, most likely, the ones that are in the book here, you're not going to run into that, but it's always a possibility to keep open, just in case. I stream math only on Tuesdays. I do stream games on Fridays. Right now we're working on Final Fantasy VII Remake. We're going to be getting into Intergrade, and then I'm planning on doing a Shinra Employee of the Month run of the original Final Fantasy VII, wherein you're only allowed to use certain classes of Mako for each of the individual characters. So, for instance, the only one that I have visible right now is Cloud. He's a pyromaniac, so he is only allowed to use fire magic and any associated fire magic. And then there also is a couple of other support categories that they're limited to. Each of the characters are limited to. So I'm going to see if I can do that. That's sounds weird and kind of interesting. But if you do want to come in on Fridays and ask a couple of math questions or something like that, I can use spare brain cells to try and figure out what the answers are to your questions. And occasionally, if I need to, I will dive on over to Microsoft Whiteboard here and attempt to answer the question a little more thoroughly. I have done it in the past a few times. So. Alright, so the Horner representation of this series that we had up here right, pi over 2 is equal to 1 plus 1/3 times the quantity, 1 plus 2/5 times the quantity, 1 plus 3/7 times the quantity, 1 plus 4/9 times the quantity, 1 plus, and then this continues on literally forever. However many sets of parentheses you need from there. I guess that doesn't need the ellipsis there because it's already covered on the inside here. Anyway. So. Spigot algorithm for pi. In other cases, we have certain values of this setup are going to have some interesting numbers, and sometimes the numbers are a little bit more easily predictable. I mean, the fractions in this case are extremely predictable, but there's a slight problem with the fact that this is what's called a mixed radix. Base. B is then equal to 1/3, 2/5, 3/7, 4/9. We'll keep going on from there. Alright, so pi itself is going to be equal to, I think, come on. With the base B being its individual parts, this is going to have a representation in the Horner, in the matrix part, as just all 2's. This is going to be a little weird, so don't worry too much about it. So we're letting you. I don't think I'm going to get this. Reduce the ith element of A, which are all 2's, corresponding to B entry, I minus 1 over 2i minus 1 mod 2i minus 1 to get a quotient Q and a remainder R. Leave R in place and carry Q of I minus 1 place left. Last integer carried from position where I minus 1 is 2 may be as large as 19. Reduce the leftmost entry A, which is at most 109, mod 10. The quotient Q is the new pre-digit of pi, the remainder staying in place. Goodness. Yeah, I'm not going to play this game. I'm already tired enough. But then, if Q is neither 9 nor 10, release all pre-held digits as true values of pi, and then hold Q. If Q is 9, add Q to the Q of pre-held digits, and if Q is 10, then set the current pre-digit to 0 and hold it. Increase all other held pre-digits by 1, 9 becoming 0. Release as true digits of pi all but the current held pre-digit. It seems like it's not that hard, but I'm just not going to get it anytime soon. I'm going to need to actually do like real reading on it. How dare. Whoa. Alright, so given a particular circle, right, find comparison between R, radius, and C, the circumference. So the pi that we want and all know and love is going to be the circumference divided by twice the radius. So since it's pi times the diameter, here we're using radius. So we're dividing by the diameter or dividing by 2r. So if you can, right, try to find some sort of like tape measure or something like that and see if you can get an approximate value for pi as accurate as you possibly can, just to see how close you can get your calculation. So find some sort of object which is not particularly stretchy but is round, and then you can get decent approximations of pi. somewhere on the order of 250 BCE, Archimedes came up with a rather intriguing way to find pi, and this was approximating the circle by inscribing it and circumscribing it at the same time. %. Perfection. All right, so whatever, close enough. Right, so here we have this diagonal, which is going to be all four sides of the inscribed square, which are all length √2/2. And then we have this length on the outside, which is the big square, which is going to be 1. It doesn't really matter where we did all this. Archimedes especially liked to attach the corners of the inscribed and circumscribed figures, whatever they might be, at the same points. Okay, so then this allows us to say if we've got our radius is known at this point to just be 1. Then he was able to get a rough estimate for the circumference of the circle . Between the larger one, which had a circumference of 4 in this particular case, and a value of 2√2 on the low side for the inscribed circle is the perimeter that's going all the way around that one. So the circumference of the circle needs to be somewhere in between those. And then if we divide all of these things by 2 times the radius is a half. Yep. So if we divide by 2r, Right, then we end up getting just 2 root 2 is less than the is less than c over 2r is pi, like we said earlier. So it's just pi here. Is less than 4 over 2 is just 2. That can't be right. Nope, it's 4. Jeez. Right, 2 times a half. So our pi value is somewhere between 2 root 2 and 4. And 2 square root 2 is 2.828. Right? Yeah, 2.828. .78. Nice. So your accuracy is probably pretty decent. Right, now if I wanted like an actual precision instrument, I do have calipers downstairs, which would be really nice to use. But unfortunately at the moment I don't have those. I mean, they're just downstairs, so it's not that hard to get, but... King Azuma, not too many more anymore. There was one guy named Taiyo Inoue, but I haven't seen him online in a long time. Let's see. Give me 1 minute here. Yeah, he's been off so long that he no longer even has a video that pops up in his videos section, which is really too bad, because he was a really good guy to do that. And Megalomorph. Man, also... Nothing? The most recent clip that he's got is from last year. I know he's streamed since then, but yeah, things are getting a little rough. Woo! Boop. No. I've only ever known like 3 or 4, probably. Oh, duh. Penn Center. That's fun. I just popped up in the while I'm offline, check out this person. So it was literally just showing me. Looks like he's also got STEM quiz and Puzzle Andy as suggestions, but I don't think Puzzle Andy probably does strictly math, but could be worth a shot. Yep, he's been doing some other random kinds of math. He's been, yeah, he's been hanging out in our stream. We've been hanging out in his. It's a good time. So anyway, Archimedes did the did this with ever more sided shapes. So he did it with square, he did it with a pentagon, he did it with a hexagon, and started just making more and more sides on the shapes. Every time you add a new number of sides, whether it be like double or whether it be just increasing the number, either way you end up with a more accurate value for the area. So if we were to zoom in here, let's take this thing, let's move it, or take a copy of it, I guess. Take a copy and put it over here. Close. Oops. Return to 100. Damn. You know what? Let's just blow it up this way. And then down. Take all this again. Whoa. Okay. Okay, so ignoring the fact that this is really just awful, which of course you can ignore, right? Just 100%, totally. So another way to, or another location where we might be able to do this is like if we were to find the tangent of the, or not even tangent, we can find this radius of this square, find out where that point is, and then draw straight lines from the sides of the circle to it. Draw a straight line. It's totally a straight line. Don't know what you're talking about. Right, so now we have an inscribed octagon. Now to get the outer one, I think it's a little more tricky. Because basically you have to draw the tangents at each of these points. And then just connect the dots between all the tangents. Oh, that was a mistake. So in theory, again, you could find the tangents at each of these lines, extend them until you find the next one. And again, this is very approximate, but nonetheless, Archimedes eventually found a way to, he made like a giant circle and ended up finding a way to get polygons that were inscribed and circumscribed with 96 sides. And so and with that, he was able to prove that pi was somewhere between 3 and 1/7, which is approximately 3.1429, and 3 and 10/71, which is very approximately 3.14, oops, it's the other way around, 08. Boo. So, you know, for what he had going for him, and the fact that he was doing such a very slow method, ended up, you know, working out okay. And if we take the average of these two things, difference between, or the sum of 8 and 29 is 37, divided by 2 is going to get us 18.5. So 3.14185. And 3.14159 is not terrible. So I mean, again, it was all geometry based. He used several. You know, he was mostly working with compass and straight edge type stuff. So yeah, it ended up not being awful, but you know, within a reasonable amount. Especially since, again, this was 250 BCE, so 2,200 years ago, give or take. Hawk Big Ice, good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. We're talking a little bit about Pi tonight because it is Pi Day. Happy Pi Day. Also, I have my shirt on. It's really cold inside my house, and I don't want to take it off, or take off the other stuff. But had our Pi Day of the Century shirts on. That was 3:14:15 at 9:26 in the morning. So or wait, 9. Yeah, 9:26 and 53 seconds. Well, his error if we were going to find it, right? So subtract those two and then divide by the actual. So pi minus 3.14185 if we just went with the average. So then divide by pi. So it's the difference in the two divided by pi. So 3.14185 minus pi equals this divided by pi. Yeah. Okay, so the experimental error on this is 0.000819159, or this is approximately 0.0082%. Now, keeping in mind, of course, right, it's only accurate to 3 decimal places. It's not terrible, but still. Alright, I think I will actually grab my calipers, and I've already got 2 glasses here, so it's easy enough to figure that out. And I don't need a tape measure. I've got the calipers, so that's good enough. Alright, so I'm gonna grab those. I will be right back. I'm gonna run a let's do a 1-minute countdown, and we'll do a 1-minute countdown, and I'm gonna grab more water because I need more water. Hydrate, hydrate. I will see you in 60 seconds to 120 seconds, give or take. And I'll let you hang out with the music as well. So, be right back. here we go. Coming on back. All right. So thanks everybody again for coming on in, and we're going to do a quick experimental Pi Day special here. I have 4 round objects in front of me, so we'll hopefully be able to figure this out and get a pretty decent value. I'm hoping for 3.1. If I can get that accurate, and again, these are calipers, so they're pretty accurate in terms of, or they're very precise. It's a precise instrument. All right, and I will be using string of some description. So I may or may not have an accurate method of measurement here. Part of the problem with this is it will stretch a little bit, so maybe I want to go with plastic. I don't think is long enough. No, it's not long enough. Zip ties. It's part of the problem of not having being arrogant enough to say, no, I don't need a tape measure. This is fine. Alright, I have a zip tie here. You can barely see it. Well, no, oh, sorry. That's a twist tie. There we go. That's the name of it. Alright, so take my coffee cup here. We will wrap the top of this with the twist tie. Oh no, it doesn't go all the way around. Okay, try the bottom. Okay, we'll make it around the bottom. Pull it tight. Hold it against the actual bottom. See if I can crimp this thing using the calipers while I'm trying to hold it at the same time. This is fine. There's no possible way in which this can go wrong. Cool. I kind of cut it up a bit. Oh, that works. Too long. Should have expected that, I guess. Okay, so we got 0 here. There's 5 inches. Lol, use centimeters. Okay. So there is 12 centimeters here. Where'd it go? There's one part of it that I really barked up with the calipers. Ugh, did I lose it? I lost it. Oh, that's it, yep. So this was 12 and 11.5. So 23.5 centimeters looks like. Okay, now if I didn't just completely read the entirely incorrect thing. Alright, so this is going to be C and R. Or diameter is actually going to be easier for me, because then I don't have to figure out where the middle of this thing is. Okay. So then to find the diameter, I'm going to open this thing up. Okay, we're going to start closing it in. Okay. I don't know that that's making it all the way around. It's the only bad thing. So let's back it off a little bit. And then we find where it's going to be at the widest. And then tighten it up. There, that's about as close as it's going to get. And again, this is kind of hand wavy, but it's fine. 6.6. Okay, our value for pi. Very approximately. 23.5 divided by 6.6 is 3.56. Nice. We can do better. So percent error, this is going to be minus pi over pi. It's going to be 13.3. Alright, so now let's try to find something else that's going to work. Oops. It's interesting. Whenever my other computer is idle for 10 minutes, even if it's watching my own channel. Ouch. It goes to or the monitor goes into sleep mode. Alright, so we're not going to be able to get much more than what we've already gotten for circumference. So, bottom of a pint glass has a diameter of 6.2 centimeters. Not going to get much more accurate than that. That is really close. I need to learn how to read the 0.1 millimeter stuff, but it's been an awful long time. Alright, so we go like this. It's because of my awesomely precise calculation methods here that we got such an awesome percent error last time. This is like pretty close to the bottom here. I don't know if, right, it might also, this is really close to the scuff mark right here. Is there even a scuff mark? Am I just making things up? Well then, alright. Let's try that again, I guess. I'm just making things up, I guess. It's fine. It may also be not at the bottom of the glass, so that may also throw things off. If the diameter is getting measured too large for going up, that would divide it more, so we'd be too low. 19. Maybe. 19.7. It's about as close as we're going to get here. Okay. 19.7 divided by 6.2. 3.177. That's a little bit better. Okay, minus pi divided by pi. Percent error is 1.14. Much better. And an aluminum can, which will be shortly filling said pint glass. Hashtag not sponsored. Okay. In case there was any doubt, you never know. Okay, that's 12. Oops. And 4 makes 16.66. I mean, I don't know if I can say it's actually that accurate, but if we're gonna round to maybe half millimeters or something like that, we might be able to pull that off, but all right, this was inside. Just underneath the lip here of the aluminum. And it looks like we are getting at least to the biggest spot here. That's about it. 5.3 or just under. So 16.6 divided by 5.3. Hey. 3 point. Loves you. Good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. All right. Subtract pi from that. And divide by pi. End up with a 0 point. Nice. Right now we are calculating pi using household objects here. 0.3029%. 0.30 for playing fair, because, you know, I don't have that many significant digits, I don't think. So I was trying to measure around the outside of a pint glass and trying to get circumference versus diameter and seeing just how well we can measure things. First one was my coffee cup. It did not go terribly well. As you can see, we had a 13% error. It's not good. So I think I have refined the technique just a little bit, and maybe we'll go back and try that one. See what I did wrong. Get the feeling it was the circumference in some way, shape, or form. Probably just got the wrong... like I grabbed it on the wrong area or something like that. I mean, how much of a problem are we talking? Like, steal your food problem, or like they just leave some droppings occasionally? Because, I mean, if it's me, I'll leave some traps out. Oof. Samantha. So this is a very nice Tort Spectacular by Foundation Brewing Company. From my wife's home in Maine. Maine farms provided the grist in this product. Yeah. If you don't have the proper, like, proper warmware to keep yourself toasty, it can cause some serious health conditions. I mean, you know that, obviously, but... So let's redo this one. How many meals do I eat a day? 3, because I've learned that if I do not eat 3 meals a day, I will either be massively grumpy or just in no shape to work, really. Or the other problem was, my father used to do that. He wouldn't eat breakfast, and then he'd go to work, and then he wouldn't be hungry for lunch. So he'd come home and eat basically 2,000 calories at home in that one meal. Not healthy. Yeah. So, I mean, the quality of food is also something that's really going to play a major part in how healthy you are as well. Because if you're eating, you know, fast food stuff, it's going to be terrible. Okay, I think that's about as good as we're going to get on that one. 6.5 and change. Yeah, so I said 6.6 last time. Seems reasonable, at least. Well, I mean, yes, but at the same time, not entirely. It'll at least knock you out so you won't be feeling it at that moment, but then it can start invading your dreams. Like when you really have to go to the bathroom in the middle of the night. Blainlin, come on, man. You can fight through this. Things suck, but, you know. Generally speaking, that's kind of how life is. But absolutely. It seems like it's a far-flung future. It seems like it's not super close. It seems like whatever, but you know, you keep working at it. And you know, I always encourage people to remind people that where'd it go? Of course. The second I need it, right? It's not going to be found super easily. I'm just forgetting exactly where it is in here. Boo. Alright, seriously, where are my notes? Talk amongst yourselves. Oh, come on now. Grr. Boo. When do we get it down? Like, when do we start really figuring out pi? Or like, when did people start thinking about it at all? Sort of two very different questions. Mm-hmm. So, like we said, who's it there? Archimedes did a pretty good job of at least figuring it out for like an engineer's purpose. I know you've probably all heard this, but in order to find the circumference of the universe to within the precision of the width of an atom, you only need about 39 digits of pi. Observable universe. So the circumference of the observable universe to within an atom. So a lot of people are like, well, that's just stupid. Like, why are we wasting all this computing time on trying to calculate pi if, you know, we only need, yeah, 5 to 10 digits is really more than enough for most people, ever. So a lot of people are like, why are we wasting all of this you know, all these resources, all this computer time, all this stuff to calculate pi? And the answer is that they're not really calculating pi to do anything with it. Like, it's intentional to take this thing and just be like, we have figured out a new, you know, some number of digits of pi, and quite frankly, we don't care how useful it is. Okay, there. They really don't. The people who are more practically minded at these companies know that what they're doing is not calculating digits of pi just for fun. They're doing it to prove that their system is better than everyone else's. It can do it, and it can do it more accurately. Just shy of 9. Yeah, that takes it down a bunch. Okay. $20.9. Yikes. Okay, so 20.9 divided by 6.6. Yeah, that's way better. So 3.16 repeated. And so that minus pi divided by pi. A 0 point. So operator error. 7981. Yeah, that's way better. Calipers. Found at your local hardware store. Nobody needs these, but you know. So glad you asked. Seriously though, I did find some other cool ones. Okay, so pi can also be found with some other weird stuff. So one of them is called a continued fraction. This actually falls sort of into the same category as that Horner Horner form that we saw earlier. This is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over. So doing continued fractions like this, 292 plus 1 over 1 plus 1 over 1 plus 1 over. And this is a continued fraction. It goes on forever. And this one is also a 1 here. And then after this point, it gets to, I mean, it just gets to be all sorts of crazy numbers. And we can't necessarily really figure out what's going on with it. There's no particular pattern because, again, this is a wow. That word just completely escaped me. Not transcendent. Not transcendental. There we go. Is there transcendental values? So, I don't know what you mean necessarily by no starting place. True, could be arrogance or ignorance. So the problem is that it's been proven that it's transcendental, so it can't be a recursive fraction. Or unless you mean recursive fraction by this thing, right? But like if you try to get different approximations, right? You got, 22/7 is a pretty decent approximation for pi. I'm in the way of that. Woo. My face. There we go. Yeah, so like you can create fractions that just keep going on and on and on, like this thing. You could create fractions that end up repeating like these, but you know, these are only approximations. They're not super great. 333 over 106 is an okay approximation. 355 over 113, again, decent, not great, but decent. Yeah, there's a whole bunch of fractions that people have used to approximate pi. I got one here that is 9 digits long. 9? Yeah. So 245,850,922 divided by 78,256,779. You can also look up the online encyclopedia of integer sequences, OEIS, which will give all sorts of approximations and other cool stuff for like values that you can get. So the generation function that I popped up earlier will actually find individual values. The Spigot algorithm will end up pulling out individual values and get like, what's the next one, what's the next one, what's the next one. But again, you can't get anything that's going to like predict the whole series of numbers. Like if I just want to know what the 5 billionth term of pi is going to be, like I can't just calculate that one. I would have to calculate all the ones previous to it. Now that being said, right, if I know what all those are and put them in as inputs, then I can get as an output what the next 1 or the next 10 or whatever are going to be. In India, they came up with infinite series in the 15 and 1600s. So there's a school, famous school in India at Kerala, which developed a whole bunch of ideas surrounding infinite series and trying to calculate values of pi, trying to calculate values of, you know, what the largest number they could come up with was. There's just ridiculous kind of stuff. The Madhava series was created in Madhava series was created in the Kerala school by Madhava, also known as Madhava Newton or Madhava Gregory or Madhava Leibniz series, because Madhava himself came up with the series independently, and then Newton, Leibniz, and Gregory all came up with their version of it separately. So this was the arctangent formula of x is equal to x minus x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus ... And again, as long as this is the infinite series, this is the sum as k goes from 0 to infinity. So infinite sum of -1 to the kth power divided by odd number 2k plus 1 times x to the 2k plus 1. As long as absolute value of x is greater, is less than or equal to 1. So if you're like, well, what use is that in calculating pi? Well, this allows us to call pi over 4. Right, because the arctangent of 1 is going to be equal to pi over 4. Which is then going to be equal to the sum of the coefficients. So 1 minus a third plus a fifth. Now there's a big problem with this particular evaluation in that this particular series converges super slowly. So it takes 50 terms for you to clear 2 digits. It's going to take 1,000 terms, give or take, for you to clear 3 digits. Prepare! Evening! So just as a small note. We try not to use disparaging language, and it's all right. I understand. We just try to move a little bit away from it. It's all right. Thank you. So if we want the value of pi, we can just multiply that entire series by 4, which again means that it's going to take longer to converge, just because it's going to have a larger value. Okay, cool. Anyway, good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. If you have any particular questions, feel free to drop them in chat. And we're going to be sticking around for another little while at least, while we're trying to figure out some interesting pi day values for pi and other cool stuff. Weird. All right. Well, anyway. So we got that one. There's a bunch of others. Let's see if we can't find a good one. Right. So this specifically is looking for small values. So we wanted the arctan of 1 will get us pi over 4. And we can only pick values between -1 and 1. So if you want your tangent to have a value that is a small number, you can work that out. And similarly, we could come up with all sorts of other pi values for it, but it's still going to just be basically the sum of odd values. So that just allows our domain to be larger. So if it's a negative x value, it just means that all of our signs are going to be switched. And if it's a positive x value, all the signs are going to be as they're written. So you could do like arctan of √3/3, for example, and try to find, well, oh crap, it's 1/√3 would be the arctan of √3/3 is pi over 6. So you just end up with the same values, but then the problem is that you're trying to plug in √3/3 into all of those x's with odd powers. So it's going to be really gross. You're going to get square root of 3 in all of them. Although you could potentially factor that out too. Alright, so then several people decided, hey, you know what would be easier is if we come up with a bunch of these things, and we could do pi over 4 is equal to 4. Keep up, come on. Arctangent of 1/5 minus the arctangent of 1/239. So John Machin used this to get the first 100 digits of pi in 1706, and it worked out to be much faster. The way that he got the arctan of 1/5 and the arctan of 1/239, yeah, it's that thing just above here that we did with the successive odd powers. Yeah, it's gross. Which Euler decided, you know what, that's not good enough. So he did pi over 4 is equal to 5 arctangent of 1/7. Not really any better. Plus 2 arctangent of 3/77. I mean, this is the point where you throw your stuff across the room because, yeah. And Euler was able to calculate 20 digits of pi with this in 1 hour. So it made things a lot faster, at least. All right, and then we get another yeah, basically. But that was the other thing, is that the way that they interacted, they were able to like do partial cancels and stuff like that, and the sum of all of these things ended up combining nicely for whatever that's worth here. But or like there was an easy factor out or something like that. I don't know what exactly. So it said in 1853, William Shanks calculated pi to 607 digits, but made a mistake at 528. So everything after 528 is complete garbage. And then in 20 years later, 1873, he brought his total up to 707, correct. And a mathematician named Nilakantha in the 1400s was able to publish a new formula for pi, which, come on, which was 3 plus 4 over 2, 3, 4 minus 4 over 4, 5, 6 plus 4 over 6, 7, 8 minus 4 over 8, 9, 10 plus, and then that just kept going. So whereas the infinite series that uses just the arctan, you know, just these alternating signs and odd odd numbers in the denominator. After the 5th term, 5 terms, that's it, it goes to 3.34. So it is not good, right? We already said it's going to take at least 50 terms to get to 2 decimal places of accuracy. 50 terms, right? So when it gets out of the 2-digit numbers in the denominator. Meanwhile, this one down here, after 5 terms, it is now 3.1396. And only gets more accurate after that. So the rate of convergence on this thing, yeah, exactly. The rate of convergence on this thing is incredible. And for how simple the actual formula is, it's super simple, right? You could remember this fairly easily. All right, and then yeah, the 4 and powers of 4 as we, or multiples of 4 as we go on through, because the next one after this is going to have 12 in it, right? Right. So all of them are going to have a multiple of 4 at some point throughout them. Right, so we like that one. That one's nice. Right, and then somebody was coming up with new ways of looking at all sorts of different problems that were out there. There was the Basel problem. Basel in Switzerland being the place where one of the big European schools was. We had this, come on, there we go. We had this sum, infinite sum, which people were trying to figure out what the value was. So this is just the sum of the squares as you're going down through all this. All right, you ready? So Euler figured this one out. So the exact sum for the sum of the reciprocal squares says that if we end up taking 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc., keep going on forever and ever and ever, you end up getting pi squared on 6. When I saw this the first time, I was like, that is bullshit. Like, what are you talking about? How are those two things even related? But yeah, I've actually, yep, it's hiding all over the place. I have seen the proof of that one. It's really cool. This also ends up finding a connection between pi and our prime numbers, so that it starts looking into like the Riemann zeta function and starting to look at some stuff like, oh well, this is going to be used in figuring out how prime numbers work. This is going to be pi is used in figuring out stuff about prime numbers. Yeah, this is another one that's easy to recall, but at the same time, it's like, you know, the fact that it's like pi squared over 6 is also one of those things that's like, wow, that's messed up. And it's not getting you the value of pi immediately. So, it may be less useful, but at the same time, it's just cool. So you could be like, huh. Ramanujan also came up with a few, which I don't think I should even bother writing because, like, it's absolute nonsense. This one? That's not too bad. This is the, right, sum. Okay, goes from, let's just go 1 to infinity. Right, of 1 over k squared. Well, not 0. Heyo. So you're going to have to start with 1. Yeah. I mean, I'm going to have to write one of these, right? So... might have to actually write in cursive. This is such bullshit. Alright. So the Ramanujan formula ends up being 1 over pi. But again, you could just make it 1 over this thing, and it's fine. So this is going to be 2 square root of 2 over 9801 times the sum as k goes from 0 to infinity of 4k factorial times 1103 plus 26,390k divided by k factorial to the 4th times 396 raised to the 4k. There's another one that's easy to remember. So Ramanujan also, keep in mind, he used to, he claimed that he got his formulas from his god. Yep, I was very disappointed when I found out his story and just how young he died, because like he was born in 1887. In theory, he could have made it to when I was born, like, but . Yeah, ended up dying super young, 32. Um, who was his god? I can't remember. Namagiri. Yeah. Oh, no, wait. His mother had a vivid dream in which the family goddess, the deity of Namagiri, commanded her to stand no longer between her son and the fulfillment of his life's purpose, and allowed him to go to England. Yeah, Hardy was none too happy with some of this stuff because he was just like, I no, you need to like show your work, and he's like, I just Namagiri tells me. Yeah. And I think Hardy was good for him, and at the same time, Ramanujan was very good for Hardy. Jesus. Later, he had visions of scrolls of complex mathematical content unfolding before his eyes. He often said, an equation for me has no meaning unless it expresses a thought of God. Yeah, it's just absolutely insane how it just, you know, fully formed in front of his eyes because of the training. Like you said, you know, because of the training for it. Not just Hardy's training, but like his own personal training that he got back in India when he was just working on his own. He went through every single book in his village that had to do with math. And then he kept like asking other people to find some, and the British soldiers would bring in some from Britain. You know, they write back home and bring some back over whenever the shipments came in. There was just so many, like the modern math stuff, like the old math stuff, and up to and including everything that they did in Madhava and Kerala, would be local. So they had books for that. Yeah, and several of the people at the department in Cambridge were not particularly charitable in their assessments of him, and it just like went to show like there was such a snobbish, toxic culture of like, you know, the colonizer culture, where they were just like, oh well, what could somebody from the colonies have to offer us? And Hardy was like, no, this is very good. But yeah, watching the movie The Man Who Knew Infinity made me want to hit a few people. Jeremy Irons playing Hardy was just an excellent pick. The guy even looks like him. I mean, you look at the old photos of Hardy and it's like, wow. Rama. I have it here. Hang on. If you want to wait for it. Oh, too late. Yeah, that's bullshit. So, Rama is the seventh and one of the most popular avatars of Vishnu. In some Rama-centric traditions, he's considered the supreme being. He kidnapped... nope. There we go. So Rama and Lakshmana worked together to gain the freedom of Sita from the demon king Ravana. It's an epic adventure that talks about that. Well, you said Rama, so, you know. Yeah, there's a decent number file video about that. That was like, you know, I mean, like the way it plays out technically is correct, but it so the way it plays out is technically correct, but at the same time, the only way it works is by ignoring the restriction on the formula. So the sum of all a sub 1 r to the m minus 1 geometric formulas is equal to, and this is going to be k minus 1. So k goes from 1 to infinity is equal to a sub 1 times the quantity 1 minus r to the n over 1 minus r. Then, if you take the limit of this particular formula as n goes to infinity, oh, sorry, that's to the n, not to the infinity necessarily. K goes from 1 to n. So you take the limit as n goes to infinity of a sub 1 times 1 minus r to the n over 1 minus r is equal to a sub 1 over 1 minus r times the limit as n goes to infinity of 1 minus r to the n. So it uses this formula, specifically that the sum of the infinite sum of geometric series, okay, goes from 1 to infinity of a sub 1 r to the k minus 1 is equal to a sub 1 over 1 minus r. But there's a caveat here because of this thing. It can only be this thing, a sub 1 over 1 minus r, when r to the n as n goes as n goes to infinity is 0. So absolute, or r to the n limited as n goes to infinity, this thing, has to be equal to 0. Otherwise, this whole thing just doesn't work. Right? You try to do it any other way, and it's going to blow up to infinity. If your r value is 1, it's boring, and this whole thing's 0. Which obviously does not make any sense, because you should at least get, r being 1, you should get an infinite sum of a constant, or something like that. Yeah, a1, right? Infinite number of a1s. But here's the crazy thing. Within the context of quantum mechanics, this works. And it doesn't matter. So the way that this only works in mathematics is that the absolute value of r needs to be less than 1. So the size of r has to be within -1 to 1 and not inclusive. Mathematically. But you watch that number file video, they'll use this formula, and they'll let r be equal to some other number. It's like, 1.6 or 2 or something ridiculous like that. And it's like, yeah, no, that doesn't work that way. But whatever. They were... Ramanujan, as well as Hardy and everybody else, was way higher level in terms of mathematics than I was. So, I'm going to give them the benefit of the doubt. But I'm still going to complain that this is not this is not the same thing, just in general. Give me 1 second here. I gotta check something real quick. Any more questions? Feel free to drop them in. Ugh. Let's see. Oy. Facing off against my wife in trivia, so I better submit this thing or else. Nice. Okay. 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 Well, I got 3 out of 6 anyway. I think she's gonna get the same 3 plus maybe 1 more. So, oh well. I didn't realize that there's one question that has to do with a film series that I did not realize was a series. So didn't get that one. All right, so what else we got? Leaning towards math or other? I've got one that I still haven't figured out. Whoa. All right, cool. That was not expected. Alright, so I got one that I have not figured out. This is another Sunil Singh one. Or rather, it is in his book, but he was not the author of this one. Credit on this goes to Alex Bellos, who is the author of Alex's Adventures in Numberland. Wait. Don't. Literally just copy paste this thing. Forget. You can definitely rotate this. No, I don't remember how. I've definitely done this before. I would have thought so, but like I'm not getting it. I'm just getting the... Can we go the opposite direction? No. Okay. No, don't do those. That's a terrible idea. Like around the top ones just by themselves. Like if I hit Shift, Control, Alt. Nope, don't do that. Wait. I don't like that effect. That's bothering my ears. Oh. Too many wobbles. or even like flip vertically would work, right? That's ridiculous. It's an app launcher. Absolutely nonsense. Okay, now that I've wasted a whole bunch of time. Come on, over here. There we go. Come on. It's totally appropriate size. That's fine. Okay. All right, so the bottle itself is 27 centimeters tall. Like I said, I have not figured this out yet. Nerkly! Good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. If you have any particular questions about math, tonight is the night. So feel free and ask any questions you would like, and we will be glad to assist. Right now we are looking at an individual puzzle. It has a diameter of 7 centimeters, and something I did not mention, the bottom also has, as drink bottles are so oft going to have, they have this little divot in the bottom here, which takes away from the space used by the alcohol itself. So there are 750 cubic centimeters of liquid inside the bottle, regardless of which side you're going to look at. So it's always 750 cc's. But if you have it right side up, then the amount of liquid that exists within this bottle measures up to 14 centimeters from the bottom. And when upside down, this 750 cc's of liquid goes 19 centimeters up the bottle. Oh, sorry. Hang on. Yeah, okay. I think the bottle is 750 cc's, not the amount that is left. Maybe. Yeah, the whole bottle is 750. Some of it has been drank. How much? Now, because I'm a terrible artist, this may be misleading. Yep. I'm learning. So, empty parts. There's 8 here. And wherever this actually ends here to water level is 13. Come on now. I don't remember where I got the super cut of like all of Ralph Wiggum's stuff. It's somewhere in my music folder. So I think you don't need to. I think that you can just say, like, based on what we've figured out, even just like the amount that's missing or the difference in like so interestingly enough, right, Sunil colored in this part and left the bottom one blank. And so I was going to message him as like, here's a piece of errata you might want to fix for your next edition. And then I was like, wait, what if that's actually not supposed to be changed? Like, what if it is supposed to do that? So because we don't have any actual measurements of the bubble itself, right? You're not going to figure out, I mean, you can figure out some stuff, but you're not going to figure out everything. Like I have figured out, let's say, so my kind of insight in this was saying that this part here, in here, is going to be identical to this part here. Now that's not necessarily all of it. That might not actually be equal to each other, now that I'm looking at it. I mean, a little. It's not necessarily going to actually work the same. I think the point here is that this could be accessible to the layperson. So it's not supposed to be something that, like, you know, you need high-level calc for. So the difference between the two is 5 centimeters, but that's all the stuff. Whoa, too far. So the difference in 5 here is telling us that I think that that's actually less important. I think the thing that's important is the difference between these two numbers. But I'm still having trouble figuring out why. Yeah, 19 to 13. Like you're shifting 6 centimeters and then that becomes pi times 3.5 squared times your 6 in terms of, like, if we wanted to actually figure out volume. I don't think you need to do this. Cool. Yeah. And take a think about this one, because I think that, like, without doing actual, you know, algebra, I think we can figure this out. I think we can figure out, like, exactly how much there is without any actual math. You know, mathematical reasoning, yes, but like algebraic manipulation, I don't think so. At any rate, yeah, I need to go. So, so let's figure out who to raid, because I like people. I mean, ish. Let's check out how Boss Lady's doing. She's working elite at the moment, and it looks like she's doing more ammonia world exploration. So, thank you everybody for coming on in. We will be back on Friday for more Final Fantasy VII. And Necroli, thank you. Thanks for stopping in. Thanks for the follow. We'll stop in, or we will be back on Friday for more Final Fantasy VII Remake. We're probably going to finish the game. Probably, I think. I don't know how long the game is at this point, but we're like, from the classic Final Fantasy VII, we're basically at the Rufus fight. So if you know where that is, awesome. If you don't, yeah, don't worry about it. It's fine. So hope you all have a good rest of your week, and I will see you on Friday or next Tuesday for math. And yeah, see y'all later. This is Obi-Wan Pez for N Simplex Pachenko. Good night.